Well, let's start talking about how we can formalize this idea. Down here at the bottom, we said, here's an integral that we could probably evaluate and figure out what it is, but how do we know it converges? And that's like going to be the extra piece we're going to add in today. We've been talking about improper integrals, and today we want to like keep going on that and maybe look at some improper integrals that we can't evaluate, but we can still say whether they converge or diverge. So we'll use things called comparison tests to do that work for us here, to formalize this idea. So I hesitate to like force you to take notes on the thing I'm about to say. Where's my clicker? I'm missing my clicker. Oh, there. All right. I hesitate to have you take notes on the things I've said, I'm saying right now. I just want to develop a little bit of theory behind here. And you're welcome to do this. I think you're capable of doing this too. But I just want to, in general, like evaluate this integral right here, just like once and for all. The 1 over x to the something integral, where p is a constant. Now, the only thing I want to avoid is, right, for now, p not being 1, just because that's a special case, right? But I think I know how to evaluate the integral if p is not 1. It looks like this. Again, this is why I said maybe you don't need to copy like word for word the notes down here. You can just trust me on the result. But of course this is what I just used the power rule. For x to the negative p, it's x to the negative p plus 1 over that new power, right? It's just the power rule. And we're evaluating that from a to b and taking b to infinity eventually is what we want to end up doing. So I didn't even finish the work because I was like, I didn't feel like it, okay? You understand? So then I plug in b and a and subtract. And then the whole, whether this converges or not, in general, depends on what p is, right? It really depends on the part that I've highlighted in blue. Depends on, since this is a limit involving b, I don't really care about the other stuff. I just am wondering, does this thing with the b, does that converge? That is, does this, as b goes to infinity, does b to the negative p plus 1 converge or diverge? Another way to write that, the argument of this limit, another way to write that argument of that limit would be this way, right? Using rules of exponents. So now just go back to like even your pre-calculus knowledge with me on this. This is a function of b. It's like a rational function, right? B to the first over b to the p. When would that converge or diverge? I mean, if p is greater than 1, like if we have b to the first over b to the second, then that definitely converges. And if b is even, if p, is even 1.1, this will converge, right? To 0. If p is 0.9, then that's a problem, right? So we'll state the result in the end. If p equals 1, obviously we have 1 over x, and the limit diverges also. And I think actually maybe we even did that problem yesterday, one like that. Here I have a as the bottom limit of integration. But in general, it looks like that if p is the only time when this integral, just in general, this integral right here converges, is when p is strictly greater than 1, right? If p is equal to 1, it diverges. See this work? If p is less than 1, then this limit will come out to be, and you can try with a few examples. Maybe it's hard to do with letters. Like try 1 over x. Excuse me, 1 over square root of x or something like that. Or 1 over x to the something less than 1, right? Right, exactly. So, or equal to 1, right? So, where? Oh, sorry. Thanks. That's right, and that's the opposite.
Okay, so why, so the whole limit converges if limit b over b?
Well, the other stuff isn't involved in taking the limit, right? The only thing that's being limited is b, right? The only thing that's going to infinity is b. The other stuff is all constants, right? P is a constant, a is a constant, so the only thing we're concerned about going to infinity is b. So in general, like, forget all this if you don't want to see it. You don't have to look at it. In the end, you can just take my word for it if you like to. But I think you could prove it, or maybe it would help to just prove a couple cases individually. Try 1 over x squared. Try a 1 over x cubed. Are you getting the idea yet? I mean, I just wanted to prove it once and for all, though.
Try 1 over x to the 0.5.
Try 1 over x to the 0.5 and see that it diverges. You'll see. You'll see. Trust me.
You will.
You will.
So p diverges if it's less than or equal to 1 and greater than 0.
Well, actually, what happens if p is negative?
Then it diverges.
Then you get x to the some positive power is really what we're looking at. And does that diverge? Well, definitely. So actually, it still works.
So if it's less than 1 or greater.
You're right. Yeah, so that's what this says down here in blue. This is like the end result of all that proof
If it's
stuff.
equal to 1, doesn't it?
If it's equal to 1, that's this case here. If 1 over x to the 1, I did that case special here because it's ln x, right?
Then it does not diverge.
It does diverge.
It does diverge.
Right. I think we did that one yesterday. So is this in blue? Is that clear?
Hey, why does a have to be greater than 0?
Because at 0, we have a little bit of an issue. We have like a vertical asymptote, don't we? If the bottom limit of integration is 0, now we're not just dealing with like an improper integral of one kind. We're like dealing with a vertical and a horizontal asymptote, and all bets are off. We will discuss that in a second on the next slide, actually. So do you understand the final statement, even if you don't understand the route we got there? I think you could even work this through if you gave it some time. I just like to justify things whenever possible. So Andrew, did you have a question too? Okay. Like I said, I wanted to prove it once and for all. You wouldn't have to. Every time you come up against like 1 over x to the 1.5, you could be like, do that fraction, see that it converges. Every time you come up against 1 over x to the 3rd, you'll see it converges. You can do the work every time you see it. But we just did the work once and for all here, just to say that they'll all converge. So this statement I have recopied over here. There it is. These other ones I might challenge you to prove in similar ways. This one answers Helen's question too. Like we were intentionally avoiding the vertical asymptote situation by requiring a to be greater than 0. We're just talking about like integrating this guy anywhere you like. Even 0.1 is fine, but some finite value and then beyond, right? So, but as soon as we introduce 0, we have a little bit of an issue. So now this one, maybe you can actually justify that one without actually going through all the proof. Notice here, this I promise, this isn't the typo, okay? This is the exact opposite situation. 1 is still an issue though, okay? When we're in between 0 and b. And the way I might justify that is I'd like maybe you to think about like, yeah, what are you doing? Yeah, the inverse, right? I mean, isn't this the exact same situation actually just running up the y-axis? Is it maybe pretty clear that if 1 over x squared converges out at infinity, as we go out as x goes to infinity, that 1 over the square root of x should converge near 0? Right? Think about the inverses if you want to justify that, or just take my word for it. Here's another statement, and we could make other statements like these, right? Did we do an e to the something yesterday? I mean, anything exponential will converge. It's not just e, right? E to the c, we could combine that as one base if we liked. But in general, if this is just saying, if you have an exponential decay function, the integral under that from any fixed value to infinity will converge. Another way of saying that too is under an exponential growth function, if you integrate back to negative infinity, it converges always. And again, I might challenge you to just kind of sketch a little proof of each of those just for fun. Because once we establish these results, we can use them powerfully to analyze other functions that might be a little bit crazier, which is exactly what we're out to do today. All right, so those are helpful results, as the title says. A lot. So this is, if c is a number less than 0, then this is an exponential decay function. Is that clear? That is, it looks something like this. Right? And I'm just telling you right now, without proof, because I said, why don't you prove it for fun, that if you integrate this from any fixed value you like out to infinity, it will always converge. If c is less than 0. If c is greater than 0, then we don't have this picture. We have exponential growth, right? And then of course it's pretty clear, you don't even need to do the algebra there to see that that's not going to work. It's a to infinity of e to the cx.
What if you have one over
Any number to the x. Again, if it's exponential decay, it'll converge.
Yeah.
So if you have like 1 over 2 to the x, that's exponential decay, right? And actually, maybe you could use this result to prove that, because I think I can write your function in this form. Then it'll be a negative c value. That's the pre-calculus for you, right? Try writing 1/2 to the x in this form, e to the something times x. You'll see. In general, we can just come out and say that though. Any exponential decay function, this will happen with. All right. So here's the first. Here's the one that we did earlier. No, actually, no. This is a little different. X to the 5th plus 1 on the bottom. It's not an integral we know how to do, right? But we can still maybe talk about its convergence. Again, if you were shooting from the hip based on our discussion in the first 10 minutes of this lesson, what would you say if you're shooting from the hip? What do you think? Does it converge or diverge? Yeah, it feels like, did anyone say that with actual gusto? Who said what? Yeah, I think we can all be convinced that it converges, but we don't know maybe for sure, so we might not know how to directly evaluate it, but we do know how to directly evaluate this integral, and we could do that if we want. We've already proved that it does converge on the previous 2 slides ago. And what's the relationship? Why am I bringing this into the picture? Because I think that's what your intuition is based on. You're like, well, this feels like 1 over x to the 5th, right? And then you might ask, how does it actually compare? How do they compare? What is the relationship between the 2 functions, 1 over x to the 5th and 1 over x to the 5th plus 1? It's actually not a shift left or right necessarily, no. It's a little more complicated than that. And the reason I know that for a fact is that this one has a vertical asymptote at negative, this one has a vertical asymptote at 0. And this one, it doesn't. That's the one proof. I'll show you a picture of it in a second here. Yeah. Sorry, say it again, Dan. Yeah, if you're thinking about Riemann sums, right, and if this one converges, this integrand, that is the function we're integrating here in red, has what relationship to the function that we're integrating in blue? Yeah, no one has said that yet, so I want to make sure that everyone hears that. Isn't this red function always, is it smaller or bigger? This one is always,
Well, the denominator is always.
yeah, the denominator is always bigger up on top, so that makes this smaller. Yeah. And here's the picture of the 2. I graphed them just for fun. Here's 1 over x to the 5th, and here's 1 over x to the 5th plus 1. And you can see that 1 over x to the 5th is an integral that converges. And the integral we have is always underneath of it. So this integral must converge too. You could even think about Riemann sum slices, right? All the infinite things we're adding up, well, all of them will be smaller, right? All right, so that's us doing the direct comparison test. Now, some of you might have heard about the direct comparison test last year, but it was in the context of series. Now, we will bring that back around, but let's just be clear. This is a direct comparison test for integrals. And actually, maybe the series result we kind of talked about, but maybe they kind of rely on each other a little bit. Maybe there is like a Riemann sum type of thing that helps us understand why they might be related. But this is, just to be clear, this is about integrals. So the first thing is what we just talked about, right? This first number 1 is the result we just used to prove the convergence of 1 over x to the 5th plus 1. Right? Because f was smaller than g. Our one function that we were trying to consider was smaller than a known convergent integral. Therefore, it converges. You see, if this is key up here. If G is the bigger thing, by the way, I just copied this right from your book. There's nothing special about this. If G is the bigger thing, then and it converges, well then if F is smaller, then it will converge too. And then this one we need to think about too, right? And this is this second situation. If F happens to be a known divergent integral, and G is bigger than that, then we know it diverges too, right? That is, if I have a function that I have in my possession that I know diverges because maybe I've already worked out the math on the interval a to infinity. And then you come along with a function, for every y value your function is greater than mine, yours definitely diverges too. Is all that second part is saying, right? Very similar to the first part. So just to clean up the last example, here's how what I would actually probably write on the last example. You see the quotes around it? You might write, since the integral 1 to infinity of 1 over x to the 5th dx converges, and this is always greater than or equal to 1 over x to the 5th plus 1 for every x value on our domain of interest, it's got to be true that this integral converges. We're not gonna say, special note, right? We're not gonna say what it converges to, but we do know it converges. Is that fair? By the way, I realize there's a lot of text in this PowerPoint.
Is the same with the small
But- Yeah, so the big picture idea here is if you're bigger than a known divergent series, then you diverge. If you're smaller than a known convergent series, then you converge. Excuse me, I just made the error. Integral, excuse me. If you're bigger than a known divergent integral, then you diverge. If you're smaller than a known convergent integral, then you converge. So, like I said, I began to say a second ago, I know there's a lot of text on here, so feel free to write what you want to write. This, like I said, I seriously, word for word, just copied this from the book. So there, this box up here. And I'm recording this too. I can give you the PowerPoint too. But did you want to look at that for another second? This is just the last example we did. That's what I would probably write if I was like you as a student, right? I would probably write that. Helen?
So it would still be inconclusive if it was greater and f of x.
Yeah. Right. Yes is the answer, but say it again.
So if f
For
of
everyone
x
else.
is greater than g of x and g of x converges,
Yeah.
then it's
We don't know anything. Right. So that presents a little bit of a limit to the power of this. But maybe we can work around that though. All right, let's take a look at an example that I definitely don't know how to integrate. Without a calculator, I think would we all agree that this is intractable? And I would venture to say that it's not just because we haven't learned enough calculus. I would venture to say that we could hand this to even the best integrator and they wouldn't be able to do it. Yet, we can still say whether it converges or diverges. What does this feel like would be maybe the first thing to ask. On the order of what? I think also again about out at t equals infinity. What does this act like? What do you think? Yeah, and what about cosine t? Out at infinity, we're kind of thinking that that part of it is somewhat negligible, right? In fact, 2t is somewhat negligible too, actually. My feeling, if you're just again shooting from the hip, is that this feels like 1 over t squared, doesn't it? Okay, that's the intuition I think we should all have. So the question is, here's our game plan, right? We think this converges, so can we prove maybe that this is always less than 1 over t squared? If so, then we're done, right? Maybe we can prove that though. What would it take to prove that? I don't know. You don't think I can prove that? I don't know. Let's see. Let's start with the result. We'd like 2t squared over t to the 4th plus 2t plus cosine t. we'd like to say that that's less than 1 over t squared. All right, I'm going to run the argument backwards here. Could I show that if I could show 2t to the fourth is less than t to the fourth plus 2t plus cosine t? Can I show that's true? That's true if this is true. Oops. And this is for t greater than. Did I write that right?
I try to think about it.
Say it again.
I try to prove t squared over that. 2 over t squared.
You'd like this to be a 2?
No, 2 over. The numerator's not 1.
You'd like this to be a 2? We can make this a 2, that's for sure. Would that make our life easier? I think that would, maybe, because then this would go away. Yeah, I kind of like that. Maybe we can use this as our logic. Okay, let's start here. The reason I wrote it backwards is so I can actually read this forwards now. Are you ready? Do you agree with this first line? That's definitely true. I mean, cosine t is bounded between -1 and 1. And for t values greater than 1, this is always the case. So we could even go back further maybe, but that's maybe a fair place to start to convince our listeners. And then that holds after that. Now I have to adjust what you said. This is, I didn't actually, all right, this follows from that. Now there's actually a 4. There's maybe another 2 in there, right? Is that all right? So this is always, and then now I'm just dividing at the end here. This is always less than 2 over t squared, and 2 over t squared converges, doesn't it? That's a little messy. Maybe we should have just like changed the problem. Take the 2 out of there, yeah. Yeah, here, let's actually go back and clean this up here. Because I kind of didn't like the, I kind of don't like the, I kind of don't like the 2t plus cosine t. That's definitely true. And then if I add, how about just t to the fourth to both sides? Are we okay with that? And then now I'm going to divide this side by this, and divide both sides by t squared as well, and multiply both sides by 2. Can I do all of that? That's what I just said here. So 2, I'm going to divide both sides by t squared, and divide both sides by t to the fourth plus 2t plus cosine t. I mean, in the end, let's just get rid of the 2 here, because maybe that's not helpful. Let's just prove that for now, and then we'll add that. We can add the 2 in. Do you agree? If this is true, then this must be true. I'm just dividing.
Didn't you just say that just give our zero to
What?
No.
No, I think we like that. I don't know. Yeah, Tyler?
What did you do to get the first line of the argument? Like, what was your thought process there?
I mean, you saw my thought process was like, here's what I want to be true. Like, how can I make that happen? So, I don't know. I'm just trying to like,
So as long as 2t plus cosine t
is
greater than
positive,
0,
which it is.
which it is.
Right.
So alright, so what you did was you set the thing less than or greater than the direct comparison. And
Yeah.
You just solved the inequality.
Yeah, I like tried to make that happen. Yeah. So since 1 over t squared on the interval 1 to infinity dt converges, and t squared over t to the fourth plus 2t plus cosine t is less than 1 over t squared for t greater than or equal to 1, the integral 1 to infinity of t squared over t to the fourth plus 2t plus cosine t dt must converge to. By direct comparison. Yeah, those are the.
Will we ever have to explain like you have like this example? Like I understand.
Yeah, I mean,
it's like less.
yeah, here's the.
Like that just.
Exactly. You don't necessarily have to justify this formally, like I just wanted to because we wanted to. All would it take is seeing that, like, for values of t greater than 1, this piece here is positive, right? Well, it's also negligible, but we can't come out and say that that's the case necessarily. It might still be true that it's always bigger than, and we don't want that to happen. We really do need to prove that it's smaller somehow. But this is always greater than 0, right? So if we have t squared over t to the fourth plus something right here that's greater than 0, then I think we can say that that's, how does that compare to this fraction? Because I know everything about this fraction. If this is greater, then this whole fraction is smaller. So that's like how the crux of what this rests on. And this is just 1 over t squared, by the way, right? So I think if we can convince ourselves that this piece here is positive, always, for t greater than 1, then we're good, right? Yeah. All right, similar, this one I think won't be quite as much of an imposition for us here. Again, go by feel first. What do you think? Yeah, since this feels like 1 over root y, we might say that it diverges, since that's 1 over y to the 0.5. So that's what I'm out to prove, and I think that's pretty quick to do, right? I'm actually just going to write it right now. Here we go. Since the integral from 4 to infinity of 1 over root y dy diverges, and maybe we actually write this, just to be clear. This is p equal to 1/2, right? For that previous result, which is less than 1, less than or equal to 1. And what would we like to be true? Let's just hope it's true here. And 1 over root y minus 1 has what relationship to 1 over root y? It's greater than for all y greater than 4. The integral we're looking at diverges too. Okay? So that's like an example of both things that can happen. And then there's something else we could say that happens that might be inconclusive, yeah.
So that's all the distribution we have to do.
Yeah. So I'm going to actually skip this one, just because we've already kind of just discussed it a little bit. We want to say something about the limit comparison test, too. This idea of, like, two functions growing at the same rate is, I think, like an intuition we have, and we can formalize that using the limit comparison test. What's that? What does it mean for two functions to have the same growth rate? Because, like, what happens when we come up against a function like 1 over x to the 5th minus 1? You're like, shoot. 1 over x to the 5th converges, and this one's always greater than that, right? And this is like what Helen was saying, or whoever was saying this earlier. Like, what do we do with this function, 1 over x to the 5th minus 1? If it's greater than a convergent integral, then we have the direct comparison test can't help us, right? So what do we do in that case? Well, we still would like to confirm our intuition somehow, and our intuition is that they grow the same rate still. Come on, everybody, they grow the same rate, don't they? The minus 1 plus 1, it doesn't matter. It's going to converge. Don't we all know that? Can't we be friends? And this is what is formalizing that. If two functions grow at the same rate, how can we formalize that? Well, If you stack them on top of each other, that is f over g, and you take the limit, then that limit should come out to be a number. Now, actually, I think it's not there anymore. But for example, if we're trying to come up with 1 over x versus 1 over x plus 1, someone asks us about the integral 1 over x plus 1. Then we might compare them using a limit, right? That is, the limit as x approaches infinity of 1 over x plus 1 comes out to be just 1. This last step here is either using precalculus or L'Hopital's if you like. I mean, you don't need to bring that in though, right? The limit of that is definitely 1, and 1 is a number between 0 and infinity. Therefore, these grow at the same rate. Why is 0 and infinity like off limits? If you get this limit and it goes out to 0, that tells you that g grows faster than f, right? If you do this limit and it comes out to infinity, then that tells you that f grows faster than g. Basically tells you nothing in both of those cases, not the thing you wanted to at least, right? But if it comes out to a number, like 1, for example, then you know they grow at the same rate. That is, if one converges, if you know one of the two converges, then the other must. And if you know one of them diverges, then the other must, because they grow at the same rate. This is, again, kind of confirming our intuition about the relative growth rate of two functions. Stack them in either order. You can put 1 over x plus 1 on top, or 1 over, right? You can do it in either order if you like. You'll get 1 either way, yeah.
So is that just because the long term
Yeah, I mean, now I'm just resorting, for this last step, I'm just resorting to precalculus knowledge to know the asymptote of that is 1. Well, you know that because as x goes to infinity, you have infinity over infinity, you could take the derivative in the top and bottom, and you would get 1 plus 1 over 1, which is 2. Did I say that right? 1 plus 0, excuse me, over 1, which is 1, right? So you could use L'Hopital's if you need, but that seems like too much firepower, right? To bring into the conversation. Yeah, Tyler?
So reiterates some of the arguments as negative exponents?
Yeah, you do whatever you want to do. All right, we were going to do that example, but I guess we're not. Like I said, the homework tonight is this worksheet actually instead of the bookwork. Just practicing doing direct on the front. Hey, Darian.
Generation Z tutoring at College Gardens Elementary is canceled this afternoon. For students who won awards at the Johns Hopkins or Scholastic Arts Competition, please come to the main office. Kern Lee, Cassie Ovitt, Vivian Zhu, Magali Nubu, and Hannah McQuaid. The Let's Talk focus group with Mr. Simpkins, Mr. Coleman, Mr. Wright, and Mr. Cooley in room 33 today at 1. Will the following students please come to the main office? Alex Santos and Gladys Gutty.
I'm going to do the last example. What did you say? Oh, yeah. Yeah, you want.
I remember that, yeah. So, Mr. Chase. So according to the limit comparison test, that means that any rational function on the bottom biggest exponent is the same. Will always be that.
Yeah, it's for any irrational exponent, actually. Yeah, but I mean, we'll see that here in a second too. Since this diverges, why did I choose that? And the limit, as I'm about to prove that I chose the right function. I'm about to prove that I chose the right function.
Okay.
That 1 over root x divided by root x over x minus 1 equals limit as x goes to infinity of x minus 1 over root x times root x. We work that out.
I found it last.
I didn't get. So, that means the answer is gonna have to be it's not sort of. So now we're taking the ratio
So that's what I might write.
if f goes faster than g, means it comes towards so we can have g goes
Lydia, Aruna, please
Yeah,
come to
so-
the main office. Lydia, Aruna,
Does that make
please
sense?
come
If we
to the
get
main
0 for
office.
this limit, then it means that then this function down here, this function down here grew faster, right?
I'll even see them, right?
So that doesn't really help us because we wanted to show that our two functions grow at the same rate. And if this comes out to infinity, that means the top function grew faster. That also doesn't really say what we wanted to say, which is that they have the same relative growth rate. But because we got 1, that means they do grow at the same rate. Or no, 1 is often going to be what we get, but it could be 2 as well or something. Then it means they grow at the same rate. If this diverged, well then so must this. Done by the LCT, right?
So can you like relate this to big